Hi everyone. Do you hear me? Yeah? Do you hear me? It's good? Awesome. It's going to be a very interesting session because you're very intimate with me. You might probably hear me breathe, but I have almost no feedback with you. It's the second time I do it. I did one yesterday, so hopefully today it gets a little bit better. Today we're going to talk a little bit about resiliency and especially chaos engineering and how we apply that to build resilient systems. My kind of work with AWS is about resiliency, right? I've been working now with AWS for about 3.5 years, and I've been working on large-scale systems for almost 18 years, right? So some of these things that I'm talking about is most of it lived through experiences and failures. And I'm going to try to give you some of these experience and then kind of ideas so that you don't have to fail like I've done before. Okay, first failure, right? My clicker, of course, doesn't work. So let me check that. All right, so I need to tell you, are you able to predict a little bit what is going to happen in this video? Do you know? How many of you have seen that? Yeah, so if you haven't seen that video, try to guess what is happening. It's very interesting, like, so you can think about this guy like being the rampant query in the system, right? It goes slowly from the client to the back end, looks very gentle and nice and friendly, and all of a sudden takes everything down. And actually the most interesting part is not necessarily the thing going down, is how hard it is to bring it back up. Right? Very often people talk about things that break down, but actually in my opinion it's a way more complicated and dangerous to bring things back up. Right, so why am I showing you this? And before I'm going to turn my Bluetooth on, that will help with that. All right, so you see that what happened. So why are we talking about that really? Well, it turns out these kind of distributed systems are really, really hard to predict. And this video, in my opinion, represents very well what a complex system is. There's tons of elements. We can imagine a lot of scenarios, but it's very, very hard to predict what will happen. In fact, we usually say that if you have a system comprised more of 10 parts, it's kind of complex because you have so many combinations of possibilities of things interacting with one another. And asking an architect to be able to predict what's going to happen is pretty much impossible. Back in the days, you had your monolith, maybe a CDN, a database. At least that's how Amazon.com was built in the early days. It was quite straightforward to understand to some extent. The problem was with scaling, right? So when we scale, then we have to break this into microservices. Now we have over 1,800 microservices running on Amazon.com, right? So it's a lot of services interacting with one another. So we need to figure out how we run with that. And you also have to remember that failures happen all the time, and especially in complex systems, right? Again, back in the days when you had 3 or 4 components, it was totally normal to have all the system to be running 100% all the time. Right? That was kind of the expected level of resiliency, 100%. Right? Nowadays, when you have thousands, or let's say 100 even, of services, it's impossible that at any point of time everything works. Right? It's just statistically impossible. You always have something that will fail somewhere in your system. And we call that kind of the idea of being able to run a complex system with failure in mind. We call that kind of resiliency. It's the capability to run with failures. And there's a particular term for that called partial failure mode. Right? And this is how it looks like, because I could explain it to you, but I think this video is much better at explaining. This is a taxi driver in India, and he just got a flat tire. Well, he has to go. There's time. The customer wants to go at the destination, and he calls his mate to bring him a new tire so that he can actually complete this mission. And that's exactly what the idea of resiliency and partial failure mode is, and this is what we want our system to be able to do at large scale, is how do you run a system so that if there are failures around, we can still do what we want to do. And sometimes we have to degrade, right? But at least we can continue doing what we want to do. So this is exactly what resiliency is. So now the question is, how do we build those systems? Well, there's tons of things. And when you ask usually people, how do we build resilient system, they'll first say, infrastructure and application. And indeed, actually the first work has to happen on the infrastructure level. You go up the stack, network and data, to the application. But what is up there? The most important thing is people, right? Because you can have all the best technology in the world. At the end of the day, it's people that will implement and run the system. So it's very, very important when you implement or think about resiliency that actually you put people on top of the pyramid and even at the center of any decision that you're going to do. So all that needs to be designed with resiliency. I'm not going to do a deep dive on resiliency in these sessions. I have several others, but this one I want to focus more on how do we test for resiliency and how do we improve through methodologies like chaos engineering. So we have those systems, and back in the days we would test those systems with unit testing and functional testing, but you can easily imagine that those ways of testing are actually not at all fit for what we want to do now in large-scale systems. There are millions of people. It's impossible pretty much to simulate tens of millions of people using a system at once, right? So we have to come up with new ideas, right? So this is absolutely not enough. And in the mid-2000s, when Amazon.com started to experience this exponential growth, we hired a guy called Jesse Robbins. And Jesse Robbins first had the best title ever in any company, Master of Disaster. But Jesse Robbins was a firefighter. And firefighters do something very interesting when it comes to training. They train roughly 80% of the time. And you know why they train? Anyone wants to get a guess? I know it's silent, but you can yell, I can hear. It's simply to build an intuition, right? So that when they go and fight a real fire, they don't have to think. They don't have to follow a book. They don't have to follow a set of rules, right? They can just react with intuition so that they first fight the fire, but actually also don't get killed. Right? If they think too much, too long, they're pretty much dead. So he came with this idea of building this resiliency mindset and learn how and teach the team how to have this kind of intuition to fight outages. And he did something quite interesting. He launched what we call game days till today. And what he did was quite interesting. He was running in data centers and then suddenly would start unplugging servers. There's quite much noise there, but I hope you can hear me still, right? He would just go around, unplug servers, and even at some point, he would shut down whole data centers. We didn't repeat that experiment too often because taking down the data centers was quite damaging. It took down some customers, so we thought, okay, maybe we shouldn't be that brutal. But it was nonetheless a very, very interesting lessons on how our system were starting to behave. But the game days was kind of an old idea and not very interesting marketing-wise. Right? I think Netflix in the end of 2014 started to expand their architecture into multi-regions. They started to grow in the number of servers, and they came up with a much better title for doing this kind of in-production test, which is called chaos engineering. And chaos engineering, the idea is very simple. It's you inject failures in an environment. Netflix does it in production, but it doesn't mean necessarily that you have to do it in production. In fact, I always say never start in production because it will always fail. So you have to start very early on in your dev environment, and I'll do some demos with you a bit later. And then you progress towards your different environment, test, staging, and maybe eventually when you're Netflix, you can do stuff in production. And these kind of injections can go from, application level, host failure attacks, stack attacks, network attacks, region attack. but also people attack. I'll give you an idea, and I'm not saying that you should break the necks of people. People attack, I've done it one recently with a customer, is that customer has the person called Paul in the company, and Paul was the master hacker. You gave him any task, he would be able to do it, fixes everything, understand everything better than anyone in the company. Paul boss factor was very, very high. And when I'm saying Paul boss factor, it means if Paul gets hit by a boss, the company could have big problems. So what we did was very simple. I arrived in the morning, I say, Paul, give me your laptop and you go home. And then let's see how the system is going to operate. 6 hours it took for the whole experiment to stop because it was already all panic. There's tons of issues. People didn't know how to recover some databases. They didn't know if there were some backups, how they were activated. So there was tons of issues like this that you could simply do it with a human attack, right? So that's kind of what we're doing with chaos engineering. And we do it really to build first an intuition towards how do we behave in a net outage, but also to find new problems, right? The testing is very, very good at fixing the knowns, right? Or testing the knowns. But it doesn't uncover the unknown, right? It doesn't tell you how system might interact or give you some, let's say, idea of what happened if you add latency in the system, you know. Chaos engineering does that, basically, right? So it means that we can uncover problems in an environment when all the engineers are at work, right? And usually we run chaos experiment at 10 in the morning when engineers had their coffees, they are ready, they are not hungry, they don't need to go to lunch. They are prepared to do some work, right? If you do it too late in the evening, usually it doesn't work. Too early, there's no coffee. So chaos engineering experiment usually start at 10 a.m. and then we break things when everyone is in the room. The problem is if you don't do that, outages always happen on Friday nights, on weekends, during Christmas, on birthdays, on weddings, and that's not what you want. So we uncover weaknesses at the right time to avoid being awakened at 1 a.m. And the whole idea of chaos engineering is really not to break things without a purpose. I always say chaos engineering is a scientific experiment to demonstrate an hypothesis, and we'll talk about this later. So what are the phases of chaos engineering? Well, there's quite a few phases. The first one is you don't start chaos engineering if you don't have resilient system. If you just have a system that you know can break easily, chaos engineering is great as a look forward or kind of give you some ideas of what might happen in the futures, but it's not for the present. If you want to go into chaos engineering, you have to have resilient systems. So you have to go through the exercise of reviewing your architecture, figuring out if there are single point of failures, if you are sensitive to cascading failures or things like this. Right? And then you go all the way to fix. And sometimes after fixing, well, you go back into the experiment and then you try again, right? Or you go back into the very beginning, starting to rebuild the resiliency because you have uncovered something which you didn't expect. So let's take a look quickly about some of the ideas to build resilience system. I think one of the most important thing about resiliency is the idea of bulkhead. Isolating a part of the system so that if there's a failure happening on one part of the system, it doesn't propagate to the rest of the environment. And this is not a new idea. In fact, it's an idea that has been used for building ships. And trying to avoid having the water being propagated across the entire boat. Sometimes it doesn't work, but most of the time it does, right? So these kind of ideas you have to keep in mind. And we use that system, or that idea a lot in AWS to do what we call sail-based architectures, where we take an environment, a full environment in a region, and then we create a sail out of it, and then we replicate that sail many, many times within the region, right? And then we do DNS routing inside the region across many sails. And some of our services like DynamoDB or S3 have tens of thousands of sails within a region, right? So fairly big. And we do that simply to limit the blast radius, right? So if there's a cell having an issue, we can isolate, we can test, we can really deep dive into that cell without affecting the rest of the environment. And I think that's an idea that is very, very powerful to build resilient system. Another important thing is to think about cascading failure, and especially overload. Now, because very often in an environment we build redundant applications. You duplicate, for example, your application, but then you really have to think what happens if one part of the application fails, and then the entire traffic goes to the other AZ or region, right? And this is, I think, a very good idea of how overload works, right? The mom is the load balancer. She's giving care to 2 kids. One of the kids experiences an issue, falls, and then she gives the entire attention back to the only left kid, and then overloads the kid, and then that fails. And that's actually roughly exactly how system fails, and most of the time that's due to overloading. And there's many reasons why you might have overload, right? So in terms of resiliency, this is just a summary. It's really not a thorough understanding of everything about resiliency, but these are some of the failures I've seen and lived myself. Certificates. How many of you have had outages because of certificates? Yeah, exactly. And it's weird we don't build alerts for certificates, right? Because it's very simple. It's check a date of the certificate. If that date is coming to expiration, sends an email, and then verify that someone reads that email. That's actually the most problematic thing, because the email always been sent. It's just no one reads it. Another one is memory leaks. How many of you have had a Saturday restart because your Java JVM instance just has leaks, and you don't really know when you say, well, let's restart it every Saturday, and hopefully it covers the problem. Licenses as well, right? And versioning. I still meet a lot of customers that don't do versioning. So that means they just deploy code, and then you ask them which version of the code is being deployed, and they have no idea. And that's a problem, as you can imagine, because then it's very hard to figure out where the bugs might be. On the application level, killers are timeouts and retries. Right? I think that's 90% of the outages that I've lived in the last 10 years are entirely related to timeouts. How many of you are Python developers here? Yeah, cool. Can you tell me the default timeout of the request library in Python? Anyone? Yeah, exactly. One person said no timeout, and in fact, it's exactly what it is. And it's not only Python, it's the same for the JDBC drivers, which are 30-minute timeout. It's the same with many of the Tomcat SQL drivers, which have also 30-minute or infinite timeout. And that's a problem, because we use libraries, we import libraries through NPM, through pip, and we assume things are built right way. And often the timeouts are not set. And when you don't have timeout set, it means that when you call a dependency, that dependency doesn't answer, and your client does a retry, well, guess what happens? You run out of connection pools very, very fast if it's a database, for example. All right, so timeouts are super important. And I would say if you are not able to answer the simple questions, what is your default timeout in the systems, then you have a problem, because that will break one day or later. Another one is retries, and especially avoiding retry storms. Right? Retry storms are, for example, my system is experiencing a small network glitch, right? And everyone retries at the same time, the request. That creates retry storms that usually does overload and kills the system very easily. Another one is if you have just an error in the backend, and all the clients start to retry and retry every second. Like, that means all of a sudden, well, your system will keep in retry loop. And what I've found the biggest problem is people don't define the numbers of retry. So I've seen a lot of systems retrying infinitely, never stopping, going to a loop, and until you actually stop the backend, it will continue retrying. So the right way, if you have retries, is to do a backoff. So system has a problem, your client makes a request, okay, you say, I'm going to retry. And then if it still has the error, you just say, oh, I'm going to back up. So you retry after 2 seconds, after 4 seconds, 6, 8, 16. We call that exponential backoff. Right? But we also figured out that simple exponential backoff doesn't work. You just have to have exponential backoff plus a jitter, so that when you have a complex systems, you don't have this kind of retries that all happen at the same time. So think about this when you implement your application. And I think a very good pattern to force the developer to think about timeouts and retry is to use circuit breakers. Right? Circuit breaker is basically you englobe a request inside an object, and that object monitors for the dependency, whether the dependency has failures, its latency and errors, and if the errors keeps coming, instead of querying it, you just break it. You just say, oh, well, don't go there, it's bad, right? And when you create that object, the developer is forced to have a kind of a second, what we call it degradation, right? So you tell it, oh, if that object breaks, then, for example, serve from cache or serve from other things. And if you've used Netflix, they're really good at using circuit breaker on the UI. They often have recommendation engines that are personalized. If those don't work, they will just give you popular on Netflix or top trending here and there. And these are all coming from cache. So it serves two things. It actually makes the backend free of queries because everything is going to go to cache. And that's a very good thing to do when you are experiencing issue in the backend. You don't want to have more people coming and making active query on your application when you are experiencing issues. So when you're experiencing issues, back off and try to give back general type of data, like something coming from cache. On the operation level, I'd say you really have to have an understanding of what's happening in the system. Right? I still see a lot of time logs and being able to trace a request or observe the entire system, really not to the point where you can very fast pinpoint problems. So this is super important, and you have to do this. Also, infrastructure as code, I think this is super important, so that you know how the system is deployed, and you can reproduce it, you can rerun it, you can version control it. So all that is very important. So if you're really interested into that stuff, do a shameless plug. This is a series of blogs I've wrote on Resiliency. You'll have all the slides, so you don't have to take the. I'll publish the slide on my Twitter handle after this talk. But you can go deep dive on there. And there's also a very good tool and white paper, what we call the well-architected framework, which is a set of questions that you go through with your company to kind of make you think and force you to think about all those little ideas and systems that help you build more reliable, resilient application. So once you've done that, you're ready to kind of go to the next level and start thinking about chaos engineering. And before you go into breaking things, you have to figure out, how am I going to monitor the health of my application? What is my steady state? And the steady state is not straightforward. A lot of people will start using CPU or memory metrics. It's totally false. It's totally wrong, even though you can have the patterns of your CPU and memory. Usually it's very local, it's not system-wide, and you have to think of a better metric. And you have to have a steady state that you can see the evolution over weeks, months, and you can compare, go back, and see what it means. To give you a very good idea of, in my opinion, one of the best steady state, Netflix has what they call the pulse of Netflix. And the pulse of Netflix is simply how many times people around the world click on the play button when they start Netflix. And I think it's a beautiful metric, because if the system is experiencing an issue, people will tend to click a few times. Oh, it doesn't work. So they can detect these kind of small changes in the number of play buttons people click. And I think this is directly related to user experience and also the business, because the sole purpose of Netflix is to deliver video, and customers want to see that video. And so I think it's a beautiful metric. At Amazon, we use the sales, right, or the shipments. This is for us very, very steady metrics. We are able to do very, very good predictions on what is going to be our sales or shipment in the particular region at the particular time. And we did some experiments on the Amazon retail page, and we increased. We added 100% latency or increments of 100% latency until having almost 2 seconds added. And for every 100 milliseconds, we noticed almost a 1% drop in sales. And 100 milliseconds is not something you can detect as human, right? Our fast humans are roughly 300, 400 milliseconds. People like me are more on the 600, 700 milliseconds. So it's more touching the behavior rather than make you being aware of what's happening. Google is obviously the search, right? And they can make experiment by adding latency into their website, and they see that if they add 500 millisecond latency, it's 20% fewer search. And that's when search is your business, it's massive, massive impact. So once you have your steady state figured out, and that's actually quite hard, you have to go into the fun part, and that's the hypothesis. And this is where you take the entire team. So you take your CTO, your CEO, your business people, your applications, your manager. You take really everyone in the room, and you ask the simple question, what if? And then you go into different type of scenarios. What if my master database goes down? Well, very often when I do experiments like this with customers, I ask everyone to write on the paper so that they don't listen to each other, and everyone has different answers. No one will say the same thing. And usually I stop the things here. I say, okay, why everyone has a different story, right? Because if you know how your system behaves, everyone should have the same story, or at least they should have read it in a book or in the application design, what should happen, right? So we make these experiments, and then we figure out what everyone is saying. For example, what happens if I take my master database go down? Very often you'll have the UI designer say, "Ooh, I never thought about that," but I would love the user to still be able to use the application. And then you have the backend guy that say, "Oh, that's not going to support." So let me ask you a question. How many of you are supporting read-only mode on your backends today? Right. How many of you have databases? Right. How many of you are in the business of running databases? Quite a few, actually. Majority is not majority. You have other kind of business. So probably your user don't always need to write in the database, right? Give you an example, Prime Video. Prime Video sole purpose is to give videos, and they have a very beautiful patterns that if the master database go down, they go into a read-only mode. You can still consume videos, but everything that is requiring the master database is either hidden, put on hold, or queued, or just simply inactivated. Right? And that's, in my opinion, something that is very interesting. It's the same with what happens if your authentication system goes down. Do you just close the door, or do you fail open? And I think those are all interesting questions to go through when you have your whole team around the table, because trust me, it will force some very hard discussions, which are very interesting at the end. So make that everyone's problem, right? You shouldn't just have backend to go into the what if, because it will tell you just a very little part of the story. Then you also should kind of avoid hypothesis when one person in the room says, "I don't know," or "Not sure." These usually are alarms, right? So if anyone has doubt that it will take the entire system down, don't try it. Verify first, make sure it's resilient. Go back to the drawing board and figuring out, because you should really do hypothesis and experiment on things that you are confident will be resilient, because that's what chaos engineering is. It's just a method for verifying an hypothesis. So then you go into designing and run your experiment, and this is the fun part. You pick your hypothesis, you have your metric, your steady state, you might notify or not your organization. I always say notify your organization, at least the incident response team, so that they don't come from a party the night before with a big headache. So everyone should be at 10 o'clock, more or less, sharp in the office, ready to kind of take on any kind of experiment that happened. And then one thing that is super important is you should be able to stop any experiment. So I've seen experiments that eventually escalated into cascading failures, and there was no stop button. So think about how you can implement a stop button. For example, instead of really taking down the database, put a proxy in front or shut down the security group. It's usually a lot easier to revert instead of restarting an entire database or having it really locked down. So when you design your experiment, trying to find interesting solutions, right? One of the good way, in my opinion, what I've seen works pretty well, and it's not the only one, to isolate and go back very fast, is using Canary deploys. So you make an experiment in a very small part of your system. You may get some 1% of the traffic there, start your experiment, get comfortable with it, and eventually increase the traffic, right? And you have to increase up to 100% eventually, because that's also when system fails, right? So I've seen system fail at 98% when basically there was too many concurrent connections, or the cache was totally warmed up and started to have some issues. So I'm going to review with you now a bit of tools, and we're going to do a couple of demos and see what kind of bananas we can feed our monkeys. So the first one, actually, which is very interesting, a lot of the time people don't know, is on Amazon Aurora. If you use our database, you have fault injection queries. So you can literally do a SQL statement to inject some failures. You can crash a master. You can do a failover test. You can do a disk failure and add the number of error rate there, and you can also do disk congestion. And the query looks like this. You open your console and you can do system simulate, right? And those are very interesting because they are revertible immediately. So it doesn't really affect the system, it's just a simulation. So that's something that, in my opinion, people should know. And I love doing this on databases because, first is because databases are often the weakest part of the system because no one touches them first. Everyone leaves the database for the last part, even when it's about testing for resiliency, making system hardened or things like this. The database, everyone is scared of touching it. So I think when you have the possibility to simulate failures, it's very, very good. So think about that one. A very interesting query that I love to run on systems as well, even locally, is that simple command, right? WRK, and basically that will launch 12 threads with 400 concurrent connections for 30 seconds on a local endpoint, for example, your health API. Let me show you a little bit how this looks like. So I have an application here running using Docker Compose, right? So my application is composed of a database. So there's a database, a master database, there's a slave, there's Redis, there's a task, it's basically a message passing, and you can query products. So basically it gives you kind of some fun things. What is very interesting to do here is run a crazy query like this, and then you'll see basically first thing is what happens here. You know what's super deadly here? What you can realize really fast is actually logging. I would say in the past 5 big outages I've seen, 2 were related to disk being full, because there was too verbose logging, or the logging was not able to adjust for example, to the traffic, or to say there was no monitoring of the disk. And usually when your disk is getting full, you don't want to keep logging. You want to preserve the system. So you should have monitors of your disk on your instance and being able to revert and to just stop logging. You don't want to go in a mode where you just simply break because you don't have data or space left on your backend. Another interesting thing is how fast are you able to answer a simple request, right? So where am I? Whoops, where did I run that? So let's run that, and now let's try to query the health API again. You see how much longer it takes, right? And you know the big problem with that? Well, if I'm behind a load balancer or Route 53, there's a health check and there are pings, right? If I'm not able to answer a ping or a health check, what's going to happen? I'm going to be taken out of the auto-scaling group or things like this, right? So when you have storms of queries or very heavy traffic, prioritize pings, prioritize health checks. Make sure that you are always able to answer it fast. And actually a good design here would simply be to force that API to be high priority and all the others maybe lower priority, and then cache it. So this is kind of an interesting discussion that you have to have. And I didn't have to do much here. Simply one query can give you already a lot of work to do. Another one that is very interesting is you can start adding latency in your network. So this is the TC command in Linux that will add, let's say, 200 milliseconds latency on your ETH0 interface. And that's beautiful. As I say, latency is deadly. You can break things with latency like you can't even imagine because usually of timeouts and because of retries, and that's a very good way to fix those issues. Another, of course, interesting tool, and this is kind of the first tool that was really done, and that was the Seaman Army by Netflix. They started building those Seaman Armies in the 2015. The first one was the crazy little monkey behind, and what it does, this monkey, it goes randomly into your AWS environment and kills EC2 instances. So you select a bunch of auto-scaling groups and you say, well, randomly kill instances, because if you design applications so that they are resilient, they should not have states so you should be able to kill them. They should be stateless, so you kill it and then it comes back and self-heals. They're able to change security group or even break an entire region. The big gorilla behind is one of the monkeys of Netflix that randomly kills the region so that you can practice a region failover. And they do this in production once a month, and it takes about 10-15 minutes for them every month to shift the entire traffic from one region to another. So it's very interesting. The problem with the Seaman Army is kind of a bit, those are first schedulers like cron jobs, and then they are integrated in Spinnaker, which is a CI/CD pipeline. So if you want to use them, you have to go into using Spinnaker or things like that. But at least the principles are very interesting, and I think this is something that you should all be aware of. One of my favorite is the KL Toolkit. It's an open source project. And I think this one is very nice because it has very simple interface and you can build extensions on top of it. So people have built extensions for all the different clouds, AWS, Azure, Google, and even their own clouds. And what is interesting here is like it feels more like a test because you can integrate it directly in your CI/CD pipeline. So let me show you how this looks like. So this is how you define. You see in the back. Can you show me thumbs in the back? So you want bigger? So basically, you can define an experiment using a JSON document here, and my experiment is take down the database. So describe what it is. I can have my steady state hypothesis, and I say, well, in normal condition, my health check should have a timeout of 15 or being able to answer within this 15 seconds, which actually is very, very bad. It should be a lot faster than that. And the tolerance should be 200. So that means the error code that is returned is a 200. Then you can implement methods. You say, okay, first, once you start the experiment, you, well, obviously take down the database. Here, I'm using a Docker environment, so run some Docker commands to take down the database. I keep the PID of that database, of that container, so that I can restart it later. And then, so I stop it, and then I run a probe to see, is my system still alive? Okay, yes, my system might be alive. Then I restart it, and then I recheck the probe, and then I have a rollback function which basically will restart the Docker container if things go wrong. And this is very interesting because you can really see in practice how it goes. So this is, again, my Docker environment. Actually, just for the sake of it, I want to show you my Docker compose. So there is a front-end API, there is a tasks, and there is an Nginx, there's a master database, a slave, there's replication between database, there's a Redis for message passing and cache. Actually, all this is in my GitHub. It's going to be open source after this talk, so you can all download and play with it if you want. There's also the chaos experiment, so you can see in practice how it works. And really, the first thing you could do actually before going that is simply go into Docker. So you'd say, okay, let's do Docker PS, and you say, okay, let's grab, and you give the save. That's the ID of my container, and you can just say Docker stop. Right? That will stop my my container. All right, it takes a bit of time, and then you can just make another request there, and you'll see now my health check will return that in fact my slave is down. So that's still interesting. 503. The problem is it's manual, and we want things to be automated, right? So that's the cool part with the framework here. So let me restart the which one? What was the ID? So let's restart that. Let's verify that it's going to come back up. So there's cache implementing here, so I'm not too worried. It's going to come back up. All right. Anyway, so let's go back to to here. My experiment. Actually, let's just test that experiment. Sorry, I make you things change. And it's very easy. You can pip install Chaos Toolkit, and it runs very nicely. And then you can just simply run the experiment. And it goes through the entire thing. It checks the steady states. Yeah, my hypothesis and the application does respond to the health check. It is a 200 now. It stops the database, and you'll see here it started to stop it. So then you can even check the health check, and you see now my master is down indeed. Continues the experiment, and it says one of the experiment here failed, right? Because I had said, oh, my health check should be a 200, and actually you see my health check in that case is a 400, right? Returns a 503, so which is a service unavailable. Simply because my database is quite critical, so I implement this kind of error code. And I think just having these simple experiments are very powerful because they feel like a test. You can integrate them in your CI/CD pipeline, and you can use them as regression tests as well. That when you change things, when people rethink about error codes, change framework, it's very good to rerun everything. So you can make tons of small experiments like this, and I think it's really brilliant. So I really highly recommend to look into this. The interesting thing is also it gives you a journal. Oops, sorry. You see, it gives you a journal that keeps track of all that, so you can then keep them. All right, so let's go back into the presentation. So yeah, Chaos Toolkit, something very interesting. I kept that in here so you can have a look. Another one that I really like, you probably have heard about it, it's called Gremlin. Gremlin is destruction as a service in a way. It's a service that you have to pay for it, but it's very nicely done. It's a user interface. It looks like this. So this is Gremlin that is installed for my account, and here you can see the different clients I have, and I have an instance, an EC2 instance, which has the Gremlin plugin. So Gremlin works with a plugin. You install a plugin, and then it starts to talk with the backend, and then you can really start to do attacks, right? So you can say a new attack, you can select your target, and you can decide what kind of attack you want. So you can say a CPU, a disk attack, I/O memory. You can do shutdown, process killer, time travel, which is one of my favorite attacks. You change the time of the backend. That's deadly, usually. I highly recommend everyone to try that on your test environment, time travel. So this is very beautiful. It's a nice UI. What I really like is there's a direct out all attack, very clear, so that if things go wrong, you can stop. So it's very easy to do, right? You can unleash your Gremlin, and then that's it. My instance is being attacked, and then you can just simply stop everything. So if you have this kind of system, you can have a Docker container you can install on your EC2 instance and all that stuff. So something really, very nice. And there's a bunch of other ones. Toxic Proxy is one of my favorite as well. It's a proxy that you install between components, and you can design what they call toxics, which can affect latency, timeouts, and it's a very beautiful, again, interface to do it, open source as well, and it's been used in production by Shopify. So it's not something you should use in your production environment, but something in the test environment to start building cool stuff. So as I say, it's a proxy. If you're into Kubernetes, there's a nice project called KubeMonkeys, and then Pumbaa, which is a very good way to attack your Docker containers. So it kind of englobes a little bit the Docker stop, Docker restarts in a kind of a bit nicer framework, and gives you all the good tools to go around that. Another one which was recently released, if you are into traceability for serverless application, is Tundra. Tundra allows you as well to add filters and modify requests on the fly, so you can test, for example, added latency. I also wrote a big blog post if you're into Python and Lambda. How do you to kind of add latency on your functions, and that's also a very nice way to do it. And then you have to verify and learn, and really it's about quantifying the results here. As I won't go too much into detail, it's pretty obvious, but the most important one, time to detect. I think one of the biggest outages I've had are escalation path and alert system failed. That was what happened, and it was a cascading failures. Oh my God, there's a big party behind. So something that you really have to monitor from the alert, time you get the alert, from the time that all clear and stable. And so quantify all the results, and then go back into when you had the hypothesis and compare to all what people had put in the papers. Very often it's going to be a very, very big difference. And again, you have to go through that discussion. Why is it so different? Why no one predicted that DNS failover was not happening as fast as people think, right? And then you will uncover some big issue there. At Amazon, we use a process that we call the corrections of errors, which is a big process with a team of principals and very big engineers that kind of go through trying to understand when the failure happened, what is the root cause. And it goes through what we call the 5 whys. You start from the outage, and then you ask questions deep and deep into why and because, why, but why and why. And we usually don't stop into only one cycle. We ask many teams to go through that 5 whys, because usually if you ask 2 or 3 people the 5 whys, you get also different type of answers. So collect all of those. This usually gives a very interesting story. One of the most important things you have to remember when you have an outage is usually not because one problem. It's usually a collection of small problems that pile to create a big catastrophic failures, right? So when you go through that process of the 5 whys or corrections of errors, try not to stop into the first problem, because very often there's things to uncover and understand at a deeper level. So collections of more questions you have to ask. I love the one that, why didn't anyone in the other team come and help if there was an outage? I think this is something that also is a very good indicator of the culture of a company. One of the biggest lessons in my whole life is that I wouldn't be on stage today if one of my managers about 8 years ago would have blamed me. I cleaned a database in production while we were having an outage. And when I'm saying cleaning, I really deleted production system databases while we were having an outage, simply because I panicked. There was some sweat coming. It was crazy thing. And I was in the wrong environment. I thought I was in test. I was in production. I ran the delete command, and you can imagine it was not nice. And when we did the corrections of error, there's never mention of my name. It was always, how was it possible that during an outage I was able, or someone was able to delete the database? It should never happen. So basically, it was a wake-up call, and we then started to build tools to avoid problems, right? Because failures will happen. You might blame someone today for doing a mistake. Tomorrow is your turn that is going to do the mistake, and you don't want to be that person that is blamed. And at the end of the day, most of the software we build are not mission or life critical. If they are, then might be a different story, but no one is going to die if our Instagram application goes down, right? So it's no reason to blame people. What we want is, learn, and especially trying to avoid failures and build tools around that. And at the end, it's fixed, right? And there's no silver bullet. You have to do the job. Do not go into a process where you find the mistakes and then you don't prioritize fixing them. Again, 2 months ago, customers had gone through a very nice chaos engineering experiment. I isolated some big problems and then didn't fix it. 2 weeks later, 19 hours outage because of that. It could have been avoided. So don't go into that. Make sure your business understand the importance of fixing these problems that you find. There's some challenges, mostly cultural, because people love their code, love their framework, love their languages. Python versus Ruby versus Go versus everything. People go into love relationship with their code, and we all treat our code like the baby. So as soon as you have hard discussions, it's going to heat up. So try to take some distance. At the end of the day, the mission is just to build resilient systems, right? And remember, people will build the resilience. You can have all the process, all the tools. At the end of the day, it's your people, right? So focus on the culture, and naturally the rest will come. Okay, and even if you use chaos engineering, it still will fail. So you still will have major failure. We use chaos engineering all the time in AWS for many different things. We still have tens of failures a day, right? And that's just how life is, right? But we have less catastrophic failures because we are able to uncover big problems. Right? So take time and think big, but go slowly. And especially keep calm when you do this. All right. Thank you very much. There's a bunch of references. And remember, this is very important. If you like that session, go into the app and give some feedback. It's very interesting for us to get your feedback, how we can improve so that you have a better experience as well. Thank you very much.